Everyone, my name is Will, and I work at Bloomberg. I'm joined here today by my colleague David.
Hi, I'm David.
And we're really excited to be presenting to you today's keynote. It's a story of how we grew a farm of rabbits at Bloomberg. I'm going to start off with that story, and then David is going to...
And then I'll continue and talk about how we built an application on top of this infrastructure.
But first of all, let's do a quick survey. It's the end of the day. Usually I'd ask for hands, but let's have some ears. So if you've heard of Bloomberg, let's see some rabbit ears. Brilliant, brilliant. I guess you're all ears for this presentation. But yeah, let's do a quick recap of what Bloomberg is. So we are a technology company that specializes in financial data and news. We have clients around the world, and they typically are financial professionals, decision makers, people that care about getting data factually and with as little latency as possible. So to facilitate with this, we have over 5,000 software engineers. These are typically brought into one of two camps, the application developers, developing applications for the terminal, and infrastructure developers that create the building blocks for those application developers to use. We have lots of data coming into our system all day, every day, billions and billions and billions of pieces of data. So middleware is used extensively, and some of that middleware is queues. So I'm going to talk about growing a farm of rabbits. It's going to be a story of how we took RabbitMQ usage from a handful of teams at Bloomberg to hundreds of teams. So I'm going to talk about the goal, the evolution of our setup, and then finish with a summary of the challenges that we had. So where have we heard this before? We provide messaging middleware as a service. This is the goal for our team. And really, you have application developers that they don't have a lot of time. They want to build and focus on the business logic for their application. So although I have I don't think they'd have any problem setting up a RabbitMQ broker and configuring it properly. It's more about the time that they use to do this. So they can use our system, and they don't have to focus on all of the nitty-gritty details of setting up a RabbitMQ broker. Some of you might be thinking, well, yeah, is it really that hard to set up a broker? And it's easy, in fact. You can set up a broker with probably one line. But it might not do all of the things that you need it to do. So at Bloomberg, we have some requirements that make it slightly harder. Obviously, the first two are given. You want high availability, and you want reliable message delivery. No one wants their messages to go missing. But we also have environment requirements, so every machine at Bloomberg needs to reboot on a regular schedule. This means bringing down everything on a particular node and then bringing it back up again. We also want to cater to disaster scenarios. So we want to be able to survive and be in business if we were to lose an entire data center. And if we were to lose an entire data center, we still want to be able to keep that reboot schedule that I talked about earlier. And it turns out our application developers have a lot of expectations of us as well. So we can pull a few rabbits out of the hat to deliver some of these. Anyway, talking about the evolution of our setup. It turns out that we were late to the party in terms of RabbitMQ usage at Bloomberg. There were already some teams that were using RabbitMQ, and they were using it in a variety of different setups. So first of all, we have the co-located RabbitMQ app. You have the broker and the application running on the same machine. You also have the case where everyone's using that default vhost, because if you have a default vhost, why do you need to create any more? And then there's the case where you do use different vhosts for each application. The one consistent thing with all of these cases were the teams that the teams were very happy to give up ownership of their RabbitMQ clusters and pass on the maintenance burden to our team. We should have seen the warning signs there. So yeah, taking that into account with our requirements from earlier, we wanted to have clustered nodes so that if we reboot one node, we're not out of business. We wanted to make sure that the queues are available from every node. So we have this HA all policy to achieve that. Reliable message delivery isn't something that you can just have on the server side. You need to be able to do things on the client. You need settings switched on to achieve that. And we wanted to have dedicated clusters, so no more of this co-locating the application with the broker. So taking all of that into account, we needed to figure out, okay, here's the infrastructure and here's the application. So where's the line of responsibility? And we drew that line here on the vhost. So to the right, we have the topology and the client API. So we let applications pick what client API they use, and obviously they're in the best place to figure out what topology they need, queues, exchanges, bindings, etc. To the left of that, we're managing the broker, the vhost, and all the policies that go with that vhost. We also lock it down as well. So we own admin for all of the clusters. We don't give admin away for any of our clients. In an enterprise system, you need to have an audit trail for changes so that changes don't magically happen on production and no one knows why or who or how. So this is what a typical broker instance looks like. We have RabbitMQ on the left. Laser, okay. And you'll notice as well we have more than one vhost in this broker. On the right, we have configuration files. These basically define what should be on any given node. And they define the vhosts, any plugins that we have, what version of the broker should be running, all of the configuration for that broker. We use orchestration to make sure that what's reflected in the config is actually what is there, and monitoring, because you need to be able to see what's going on. Inside these policies, we quota things like connections, memory, and queues. This is our way of containing how much resources any vhost can take up. And at this stage, we kind of came across our first set of challenges with RabbitMQ. We had a lot of other challenges, but this is RabbitMQ Summit, so I'm going to stick to RabbitMQ challenges. So this first one came up earlier in the panel, dealing with disconnects. It might be fairly obvious that if you get disconnected and your application is using RabbitMQ, you need to reconnect. And as I mentioned, we run clusters where one of the nodes can go down, you're going to get disconnected. So it's important that your application reconnects when that happens. It doesn't mean that we have an outage, it just means that one of the nodes decided to disconnect you for whatever reason. So you should reconnect and end up at one of the other available nodes. It's also important for your application to redeclare any topology that it had, that it relies on. Queue syncing. This was a bit of a gotcha for us, because if you go and look at the small print for this HA sync mode automatic, you'll notice that it's not for free. When a node comes up and needs to synchronize, it's going to lock up that queue on the entire cluster. And most of the time, good clients will keep those queues to a minimum size. You'll notice this not in the normal case, but in the case when you have a lot of messages in a queue and you bring up that node. Resource leaks. So it wasn't uncommon for us to go without, pretty much every week with one of the nodes in a cluster looking at the memory skyrocketing off to the moon, and then we would have to kind of bounce that node. We developed a script called the hammer, which we hammered down that node. We have some other scripts as well, which I'll get to later. So yeah, how did we deal with these challenges? Disconnects, because it's a corner case, application developers generally don't test for that. So we made it happen a lot more frequently for them in the development environment. We made disconnects more than a daily occurrence, and this really trained their application code to reconnect each time. We were in a good position to be able to do that. These last two, these were really issues that we dealt with through upgrades. So we knew we needed to upgrade because you get better, well, these problems were fixed. The queue syncing, I believe, used to happen one message at a time. You can do that in batches now. And resource leaks, this was a bug that was fixed. So at this stage of our evolution, we had tamed the rabbits that we had in the wild, and we kind of knew what we wanted to run with going forward. But it was painful. Those configuration files I talked about, they were hand-rolled. So onboarding a new client, we would have to make some manual changes, roll them out, and then that was pretty slow. So I'm not going to go into all of the details, but we spent a long time building a self-service system where application developers can come along, they can click, register a vhost name, and then a quota, and they get that for free. They get an endpoint that they can connect to, and they can go off and develop the application in whichever tier they need to. This is where we kind of came across, and I hinted at it earlier, the next challenge with Rabbit, which was that one does not simply upgrade RabbitMQ. So it's been talked about earlier, but there's three options that you have. Full stop, this is basically an outage. You bring down all of the nodes. You used to have to bring them up in the reverse order. You don't anymore. But this is an outage. We expect our application developers to write applications that run 24/7. If the infrastructure doesn't run 24/7, then they can't do that, right? So that's not an option for us. The rolling upgrade, this is something that has become more feasible, but you can't do it all of the time. You can't rely on it all of the time because there are backwards compatibility, incompatibilities every now and again, and you have the kind of Erlang issue as well. So blue-green is really where it's at. And if we look at blue-green, these are the steps that you have. This was good, but it didn't work for us because of number 4. So I said before, we load up our brokers. We have multiple vhosts running on a single broker, which means multiple teams are using that one broker. So being able to synchronize all of those teams and get all of their consumers migrated across to a new cluster all at the same time isn't something that we could do. So we needed a solution to that problem, and we built our own using a proxy. We built a proxy that understands AMQP protocol, and using the protocol, we fish out the vhost, which is the juicy piece of information. So using the proxy, we can say application A should go to broker A, and application B should go to broker B, using the same proxy. And we can drive that proxy with whatever mapping we want for those vhosts. So this is good because before you would kind of upgrade your broker in one shot with all of the vhosts on it all at the same time, which is quite risky really. With this you can upgrade vhost by vhost, so you can manage that risk a little bit more easily. You can also do load balancing as well, so if one broker is running particularly hot, you can move some vhosts over to another broker. It also locks down, it enables you to lock down the broker. The only thing that needs to connect to it now is the proxy, so you don't have to expose each broker to your clients anymore. But yeah, there's some downsides. It is an extra point of failure, and there is additional latency. But these were small prices to pay. So I talked earlier about load balancing, so let's see how that works. So let's say we've got this application, it's in broker A, and we want to move it across to broker B. So how do we do that? First of all, we use some orchestration. We create the vhost. This is just registering the namespace, putting those policies there that I talked about earlier. So we're ready to kind of move everything over to broker B. We then do something a little bit weird. We freeze the vhost. So this is freezing all of the data flow between the application and the broker. If we disconnected the application, we've already trained them to reconnect again and again, so we don't want that. We just want to freeze them and prevent them making any changes to the state. Then we can safely transfer the topology over and then shovel the messages across. And now we can update the mapping and disconnect. When the application reconnects, they're now in broker B, and we can go and clean up any state that we had in broker A. So yeah, this solved our, well, it's very similar to blue-green. This solved our upgrade problem. And these disconnects, the whole transition of moving that vhost over typically takes less than a second, so it's not a huge price to pay for the application. It could be optimized as well if we had more details about the consumer connections and the publisher connections. So yeah, we're now at the stage where we'd kind of solved a lot of our problems, and we had more vhosts. There was a lot of vhost growth. To make the same joke as the one earlier, we grew like rabbits grow in the wild. If you offer self-serve at no cost, you get lots of vhosts. And with more vhosts means more brokers, and as the song goes, more brokers, more problems. So this is kind of more up to date with where we are today. Network partition strategies. So when you operate on the scale that we operate, you don't want any one single event to knock out or affect multiple brokers all at once. And if that event can happen, such as a network partition, you need an automated strategy to deal with that. RabbitMQ offers such a strategy, and ideally, we would want to pick the pause minority strategy because we care about consistency. We don't want to lose any messages. Unfortunately for us, we had a lot of problems with pause minority. We couldn't get consistent behavior, and we think it's down to this rebooting of our nodes. We tried changing the makeup of the cluster using forget node to try and paper over that, but we couldn't get consistent results, so we had to develop our own solution. Queue misbehavior. So every now and again, you do get queues that don't behave as you would expect. So in this case, we have a queue that has 0 consumers, but yet there's actually consumers connected to it. For these types of problems, you need 2 things. You need detection to catch the problem in the first place, and then some kind of remediation to deal with it. It's generally something that you would need and you would want your clients to have, to know that they have a queue here, it's got messages coming into it, but those messages aren't being consumed. So you have some kind of standing queue. So alarms go off, we see this problem, and we use, well, we have a snipper tool. We have a snipper, a zapper, a sinker, and the hammer as well, to deal with these types of problems. And you have to know which tool to use to fix. And this is the big one, truly achieving reliable message delivery. Typically what happens is you have clients coming to you saying, so I use RabbitMQ, and it lost my messages. RabbitMQ gets a really bad name because application developers, they come along, they pick up RabbitMQ for the first time, they use one of the clients, and reliable message delivery isn't on by default. So they end up losing messages. They don't have various settings switched on. And whilst you could go in and turn on tracing and figure out exactly where the message is getting lost, we have a checklist for our clients, and we go through this checklist with them, which 9 times out of 10 will remediate the problem. Producer confirms. This is important because once you send that message to the broker, it has to go around, well, with the classic queue case, all of the nodes in the cluster before you get that confirm back. So let's say you get the confirm back, and then you have that disaster scenario, your message is still on the broker, and you're safe. David's going to cover consumer acknowledgments in just a minute. Dealing with dead connections is something that happens quite a lot. It's a case where you often have maybe a consumer task, and all it's doing is getting messages from a broker. If it doesn't get messages from a broker, it's got no business. Unfortunately, you can lose the connection between the broker and that task, and if that happens, it's just sitting there stuck waiting for something to happen. It doesn't necessarily always trigger an exception in the client API. So using something like heartbeats will protect against that case. It's also the case that you can publish to an exchange, and that exchange has got nowhere to put the message. We saw that in Jack's presentation. You get pretty good performance if you do it. But if you do care about those messages, you can have a DLX, a dead letter exchange, to catch those. So yeah, in essence, reliable message delivery is not on by default, and this is one of the biggest problems that we see again and again and again. Coming up with the summary, so we started with these challenges, and we're kind of left with just these now. And if you look at these, a lot of these were fixed by the community by upgrading, so it is really important to go to that next version, and 3.8 looks like it's got a lot of good features to boot. Network partition strategies, well, we might not need these anymore if we've got quorum queues. Reliable message delivery, though, we need to do some work in the clients. We said it before in the panel, it would be great if we prioritized reliable message delivery over performance by default. I feel like more application developers would lose less messages. So, speaking of application developers, I'm now going to hand you over to one that works at Bloomberg. Give it up for David.
Thanks, Will. So now we're going to switch gears a little bit and take a look at how my team built a financial application on top of this infrastructure. And in particular, I'm going to focus on how we scaled up this application. So just some brief background before I get into the technical details. I work on a derivatives market data team at Bloomberg, and for those who don't know, the derivatives market has grown really rapidly in the last 20 years. So in the graph on the right-hand side, you're looking at the market size over time, and you can see that in recent years, the market size has grown to well over $500 trillion. To give you some perspective of what this number means, the graph on the left-hand side shows this value compared to some well-known market sizes, such as the US stock market. So as an engineering team, we're now posed with the problem of how do we build a system that is capable of handling billions of requests every single day? On top of that, we also have a second problem. We're dealing with some pretty complex data. So the first reason this data is really complex is because we're a centralized market data provider. We're returning data from a lot of different areas like inflation, credit default swaps, foreign exchange. Each one of these has its own nuances and intricacies. The second reason the data is very complex is because it's multidimensional. So in the images on the right-hand side, you can see examples of what I'm talking about, like a interest rate yield curve or even a three-dimensional volatility cube. If you combine both of these factors together, you arrive at my team's overall mission, which is to honor a high volume of market data requests in a reliable manner. So it's with that mindset that we began our RabbitMQ journey. I'm now going to walk you through our process of adopting RabbitMQ, walking you through why we chose it, and how we addressed one core problem in particular, which is complex routing. So what is this complex routing problem? The first thing to know is that while my team owns one market data service, this service is actually deployed to a lot of clusters. And there are several reasons for this. The first is that given that we expect billions of requests every single day, it makes sense we wouldn't want to put all of our eggs into one basket or one cluster in this case. The second is that there are security and privacy policies in place that prevent certain market data requests from intertwining with each other. So given both of these, we came up with a setup where each cluster is roughly responsible for a given financial data workstream. The natural challenge that then arises is that each application needs to control where its market data request is routed to. And when my team arrived at this problem a few years ago, we found this network particularly difficult for three main properties. And these were that the network was granular, large, and flexible. So let me get into what I mean by each of these terms. Starting with granular, it's not just a one-to-one mapping between each of these applications and one of our clusters. In reality, each application needs to have control over every single request and where it's routed to. And this is happening at a millisecond level. The second feature that made it difficult is that this network is very large. So while I only have 4 applications shown here, in reality, there are thousands of applications running at Bloomberg connected to our hundreds of service deployments. So you can imagine this grows really quickly. And finally, on top of both of these, this network is constantly changing. So just as a service provider, we are changing our deployment, so are the application teams. So on any given day, this network changes, and we need to be able to adapt to that. So in summary, the solution we find for this complex routing problem needs to be able to handle all 3 of these properties. And it's for this reason that we arrived at RabbitMQ. So with RabbitMQ, we were able to still preserve the complex routing happening behind the scenes, but we could really focus on the part that was relevant to us, which is the endpoints. So let me show you what I really mean by this and walk through a very brief example. Let's say an application would like to send 2 different market data requests to our service. The only thing that it needs to do is populate a routing key with the appropriate service ID. Once it does that, our topic exchange handles the rest. So let's say application 1 would like to send to our blue cluster deployment. It populates the routing key. That message is sent to the topic exchange and routed appropriately. For the red message to our red cluster, same deal. Populate the routing key, and everything else falls into place accordingly. Let's say someday in the future, we would like to bring up a new purple deployment. Well, the application can follow the very same logic. Populate the key, and everything else is the same. Uses the same connection to the exchange, and the message simply arrives at the intended destination. This was really useful to us because we were now able to focus on the relevant parts. The producer, where we populate the message body, and the consumer, where we declare the queue. Everything else in between is handled for us, and we don't have to worry about it. If we fast forward to today, my team has found RabbitMQ to be a huge success story. So looking at the graph shown here, you're seeing the number of messages we publish over every single week. And in recent months, this value has reached well over 200 million messages every single week. And at peak times, this is reaching tens of thousands of messages in just 1 second. And so that leads me to my second topic, which is how did we scale RabbitMQ up out of the box? And to do that, I'm going to focus on one particular aspect of our architecture. So in the diagram before, you saw our original setup, which was applications directly connecting to the vhost. And while this was enough in the beginning, as our team grew and the number of applications calling us also increased, we ran into a few problems. The first was that we just lost control of the connections made to the vhost, and this manifested in 2 primary ways. The first was that we lost control of the types of connections. So many of you probably know there are permanent and temporary connections. Well, when we directly exposed the vhost, applications were free to make any number of temporary connections to our system, and this would ultimately lead to some pretty wasteful connection churn and undermine our performance. The second way this issue manifested was that we were vulnerable to exceeding our policy quotas. So in Will's talk, you saw every vhost has a policy, which usually includes a quota on the number of connections. By exposing the vhost, we completely made ourselves vulnerable to violating this policy, so as shown here. And a second issue that we ran into was exposing a lot of information to the client. As you may also remember from Will's talk, in order to contact the vhost, the application needs to use a certain client API, client library. Well, in our case, our client library contains a lot of details, like how do we populate the message, how do we handle acknowledgments. It's something I'm going to go into further detail later. But for right now, what's important is that this ultimately hindered both sides. From the caller point of view, now their development was tied to our library rollout. And from our service point of view, now it made it harder to make changes to this library, and we were also revealing a lot of details that should be hidden from our callers. So it's with these 2 issues in mind that we added a new component to our infrastructure, which is a gateway. And now the gateway is the only component connected to our RabbitMQ setup. So let me show you how all of this comes together. Just as before, an application is sending a market data request to our system. What first happens is that message is sent to the gateway, which forwards it to the exchange, and the exchange routes based on the routing key. Now our message is sitting on a queue dedicated to that work stream. An available consumer can then take up that request, generate the market data, and populate a response. And that response containing the data is sent back to the same exchange, placed onto a private response queue, and then the data is returned to the caller, which can proceed with its higher-level business logic. So this is how all the pieces come together, an overview of our system. Now I'm going to go into more detail of how did we scale this system up. And in particular, I'll focus on the individual components and leverage a few examples from our financial domain. So the first relevant example from the financial domain is taking a look at the kinds of traffic my team receives. So in the graph on the left-hand side, you're looking at the number of requests we receive over the course of a typical day. And it really stands out how spiky this traffic is. In particular, you can see a huge spike at around 5 p.m. This could be for a lot of different reasons. Maybe one of our callers is running a huge batch job after the stock market closes. Many different reasons. But from our perspective, one key challenge we need to take on is how do we take in as many messages as possible before dropping them? The primary way we tackle this is by scaling the number of gateways connected to our exchange. While one gateway can surely handle a lot of market data requests and ingest them, it has its limits, and so by scaling the number of gateways, we have the flexibility to adapt to different throughput needs. The second financial scenario that is relevant here is that, again, given that we're a centralized provider, we are returning data to a lot of different teams. Some might be running highly interactive UI applications, and others are running longer back-end batch jobs. And so to drive that point even further, the graph shown here is showing the average response time we give to our different clients at a high level. Well, in order to honor these different SLAs, the primary way we do this, tagging along on Jack's talk, is by scaling the number of consumers dedicated to that work stream. And by doing that, we can drastically reduce the latency for any given client. So while this might be a simple technical idea, from a business perspective, this offers enormous value because we can now adapt to each new client's individual SLA and needs. If you take a step back, you've seen why my team chose RabbitMQ to handle a complex routing problem and how we scaled it up to handle the unique financial scenarios. I'm now going to conclude with the final topic, which we've all been talking about today, which is message reliability. And in particular, I'm going to draw on one point from Will's checklist, which is consumer acknowledgments. While many of you probably already know how this works, I'll walk through a brief example of how acknowledgments are used in our system. So as with before, an application is sending a request to our service. Everything in the beginning is the same as before. The message sent to the gateway, the exchange, routed, it's sitting on the queue. Everything you've already seen. But now, when an available consumer takes up that message, we don't actually immediately acknowledge it. It's still sitting there. So in the detrimental event that our consumer crashes while processing that message, maybe the data is not in the database, message is constructed improperly, well, even if it does crashes, our request is still sitting on the queue, and the next available consumer can take it up, as shown here. And let's say in this example, we are successful. We generate a message, and only then do we return the response to the exchange, acknowledge, and then the application has its data. It's unaware of all of this happening in the background. It can just simply count on reliable market data. Well, as with any simple solution, there is the opportunity for a backfire. And in our case, we have a pretty infamous one, the poisonous message. For those who are fortunate enough to not have to deal with poisonous messages, let's take a look at how a single poisonous message can take down our system. Well, this poisonous message is sitting on the queue. It arrives at our service, and in the process of processing that request, we crash. Maybe, again, there's a corrupt request, any number of reasons. But now the interesting part is that the logic we put in place to provide reliability is now undermining our entire system, because that request is repeatedly sent to all of the available consumers, and quite quickly, just 1 out of billions of our market data requests manages to take down all of the consumers. And for a team that promises 24/7 high availability to all of our callers, this was really scary and unacceptable. So in response, we considered several solutions. These are shown here. The first is just to NAC, or not acknowledge, all of the redelivered messages with the redelivery flag on. And this would have handled a lot of our cases. You know, the poisonous message case just shown here would have been tackled. But in our Bloomberg use case, we have seen that there are actually a lot of scenarios where it's somewhat reasonable for a message to be delivered twice. Maybe the machine was being turned down innocuously during the first time being processed. So we are also aware that, obviously, as we've all talked about today, in 3.8 there's quorum queues, and for our interest there is a redelivery count in these quorum queues. This would be really useful, but of course, as you've seen in Will's talk, there are a lot of challenges in our upgrade process. So we went with the third route, which was essentially to take matters into our own hands and implement the redelivery count ourselves. So let's see how we did that. To implement the redelivery count, we added yet another component, which is a Redis Cache. And so when any message arrives at our queue now, it reaches one of our service consumers. And while it reaches the service, the first thing it does, it just look at the headers, extract the unique message ID, and then contact the cache and place that unique ID in the cache, along with a count saying how many times have we seen this, and a TTL for some bookkeeping purposes. So in the event that this is a poisonous message and we do crash while processing it, we still have that information on hand. And with our acknowledgement logic, when it is redelivered and sent to our second instance, it does the same thing, looks at the headers and updates the cache with a count. We've now seen it twice, and we crash as expected. Fortunately, when the message arrives at our service for a third time, we're now prepared. So when it arrives, our service goes to the cache and sees, hey, we've exceeded a certain threshold. With this knowledge in hand, the service can safely acknowledge the request before processing it, and thus, this harmful message is removed from the queue, and our remaining service instances are preserved, and they can handle all of the subsequent market data requests sitting on the queue. So to conclude, some takeaways from an application developer's point of view. Over the course of our RabbitMQ journey of solving the routing problem, scaling it, adding acknowledgments, the first takeaway we have is that RabbitMQ is very scalable for our Bloomberg use case. You saw it tackle a very large routing web, as well as handling 1 billion per day throughput. The second is that it was very flexible. We could configure the topology to our business needs and place acknowledgement logic that met our reliability requirements. And the third is that it's very well maintained, especially given that we're operating on top of a very well-groomed infrastructure. As described in Will's talk, we can be rest assured that our application is up, highly available for our market data callers. And with that, thank you, and we'll take any questions.
Thank you, David. Thank you, Will, for sharing some of your insights on that. So it's a great opportunity to ask some questions.
Thank you for your talk. So I have a question. Assuming that at some point you upgrade to 3.8, right? So let's ignore the upgrade path for now. What in quorum queues would be missing for your specific needs? Any extensions, any missing features, any limitations? Why wouldn't you use them, basically?
Well, first, I mean, I was speaking with Jack about this last night. The absence of a big red button, which it seems like you might already have, but like if you were in some crazy case to lose quorum and you lose those nodes forever, is there some way to add another node on, replicate to that node, and then be back in business? So using the CLI, I think we tested with this earlier in the year, and we didn't get consistent results with it, but I think it's been updated since.
Yeah, so there should be a way to add a node. Tell that you need to tell a quorum queue that, hey, you can place replicas on this node, and it should work. If it doesn't, please let us know how we can reproduce it.
What is your custom solution? What is your custom solution for the network partition handling?
I was hoping no one would actually ask that. I would describe it as babysitted auto-heal. We actually handle and minimize the risk of any kind of inconsistency by shutting off. We detect our own majority and minority partitions and shut down minority partitions manually. We disconnect all of the connections into it. And then auto-heal to kind of stitch the cluster back together.
How quickly do you detect that? Do you then manually copy the messages of the minor ones over there?
Yeah, it's complicated, so yeah, we can talk about it later.
We can actually engage like a Splunk. So, then in that sense, you can get overview of network partition among all the nodes. So in that sense, take a majority of the view and knock down the, the problematic nodes. Okay.
Question here.
I do have a question for you. Sorry. In terms of the quorum, right, can you actually dynamically adding nodes when you actually, so do you actually rely and write some plugin? So in a sense you can,
So there is a new CLI tool in 3.8, RabbitMQ-Queues. You use it for a few things. You can, once you have a new node in a cluster, quorum queues will not automatically add replicas on them. Why is that? Because if you have a 5 or 7 node cluster for availability, you don't want to replicate to 7 nodes. Like otherwise, you would be running into the same efficiency issues as with classic node queues. So you have to use that tool or a different API endpoint we can introduce, doesn't matter, to allow quorum queues to place replicas on that node. You can also remove a node. If a node was decommissioned, you need to tell quorum queues, hey, don't expect this to ever come back. And it can potentially now reach a quorum, for example, and continue. Again, these decisions can be automated, but we, as the RabbitMQ team, we cannot make them for you. And of course, you can add a node on the fly, so to speak, and place more replicas on it if that's what you want, and it should work. And if it doesn't, again, please let us know how to reproduce.
So in that sense, do we need another event queue just being processed by the quorum queue? So in that sense, you can dynamically processing what happened within the cluster, right? So if you want to knock down the queue, you probably need to send a message. Sorry. Okay, all right.
Oh,
Okay.
should we?
One last question.
Yeah, Will, in your portion, you spoke about a desire or request to have the default queues have some more safety features versus being highly performant. Am I with you there? Would you envision that enhancement being made on the language client side or on the broker side? And how would you like to see that?
Whilst I think that really the right place for it would be on the client side, it's something very difficult to achieve. Maybe there could be some kind of policy that says don't accept connections unless, like, I don't know how you would do this, but like mandate that all channels have to be in confirm mode, or disabling features like auto-acknowledge, but it's difficult to do, and it doesn't solve all of the types of problem. Like the Reconnect problem, that really needs to be in the client library. So I really think it's going to take a lot of PRs to, it was great insight to see earlier the different APIs in use and which ones would be good ones to target for upgrading, or having some easy way for an application developer to come along and pick it up and get reliable message delivery by default.
Right, thank you very much.